Okay, let's go ahead and get started. All right, maybe, is that better? Okay. You hear me in the back? Is that good? Microphone? All right, perfect. Okay, so today we're going to finish going through the relational algebra stuff that we're going to do. And yeah, that will be it for relational algebra. It's not to say that we won't still reference it here and there maybe, but this will be the extent of the relational algebra that we will learn in this class. Other announcement, next Thursday, don't come here, because I won't be here. Vineeth won't be here, Kavio won't be here, neither will Hamil, no one will be here. So next Thursday, we give you the block of time available. So if you want to take your midterm during that time, you can. So there should not be an excuse that you don't have time to do it. So yeah, just don't come to class next Thursday. We still have class Tuesday, but next Thursday there's no class. It's just time reserved to work on your midterms. And we'll make an announcement about that on Piazza as well. Sometime tomorrow, probably closer to the afternoon, the midterm instructions will go online live as well. Those will be on the website, so you'll be able to look at those under the assignments tab. And that will be all the instructions and information you need in order to do the midterm. And then the midterm will be available next week for all of you. Okay. Let's just go ahead and dive right in then. So we talked about these basic ideas of relational algebra on Tuesday, and one of the areas that we didn't cover yet, that was part of the original kind of standard library of relational algebra, were joins. And joins are really going to be the area that I think might give all of you a little bit of heartache when it comes to relational algebra, because in, let's say, when you write your SQL code, the way you write joins is a lot more straightforward. In relational algebra, you have a lot more, a much greater broad range of ability to write joins in very particular explicit ways. So we'll talk about what those are and what they look like. But at the end of the day, it's all doing the same stuff. So in particular, one of the things that is a nice insight that you get when you do relational algebra is you come upon the idea that joins are nothing more than just a cross product with some sort of filter on them. That's not to say that the relational database system does a cross product for a join. It almost will never do a cross product for a join because it's computationally ridiculous to do that. Of course, you have like 100 rows by 100 rows. That cross join is not that expensive, but once you start getting to the hundreds of thousands of rows, millions of rows, a cross join can just bring whatever computer you're using to a crippling halt. So relational database systems are typically smart enough, they are smart enough to know what type of pre-filtering and other logic to apply so that when you do your joins, it doesn't do the cross product, but it does a lot of other, uses a lot of other algorithms to get that information, hashing techniques, tree techniques. It'll do pre-filtering of tables and those type of optimizations in order to be able to perform a join without having to do a cross join or a cross product for the tables. So to that end, we'll take a look at three of the three different ways in order to write what we would know as an inner join. Those are the theta, equi, and natural joins. And then after that, we'll look at the outer joins that you have with available to you in relational algebra. Note that, I'll cover this again a little bit later, but a self join is, and also the cross join or the cross product is neither an inner or an outer join. It could be both, depending on the context and what you're filtering on. So we'll look at, those are kind of separate. So we'll start with theta, equi, and natural join, and those are all three types of inner joins. Okay. So a theta join is sort of this catch-all inner join where it says, okay, you've got two tables and you want to join on some value and that, or some predicate, and that predicate can either be an inequality or an equality. It doesn't matter. A theta join gives you this way of applying some sort of logic to the join method. And when you're looking at writing it in relational algebra, both these ways up above are equivalent. You can write it with using the join keyword and then the C, which is the predicate for whatever conditional you want to apply to it, or you can write it using this cross product with like essentially a filter on it, like a selection. So these are two equivalent ways of writing it. Typically, you'd write it in the left-hand side that way is the typical way of doing it, but it really doesn't matter which way you want to write it. In this case, like I said, C is this sort of like catch-all for whatever type of logic you want to apply, and this is pretty much your standard select from where clause where you're doing a join and you have some sort of condition. It can get confusing because theta join is a lot like an equijoin in that case, where it's the equijoin you'll see uses the symbol of theta, but a theta join is just some sort of condition that you apply to a join, and it neither be an inequality or an equality. So that's what you can think of it as. And here's an example of it. So here we have the tables U and V, and they have the attributes ABC and DBC. If you're going to do a theta join on A being less than D for relations U and V, this is the result that you would get. Might be a little bit confusing to look at, so just to make it extremely explicit, here we've taken the cross join or the cross product of both these tables and then applied the A less than D inequality filter on it. Again, this is not what typically happens. The relational database system is smart enough to not have to do this, but in essence, this is what we're doing. We're taking the cross product and applying some sort of filter on the tuples, and that gives us our relation down below. Interestingly enough, you can also take this a step further if you wanted to apply additional logic within there, which is completely valid, and you can do that as well. So in this case, we've added the equality condition that table U attribute C must be equal to table V attribute C, which removes the middle tuple. And we're left with these last two tuples. Any questions so far on the idea of the theta join? Should be all very, very simple because you've done these type of inner joins before. It's just the nomenclature is a little bit different. But this is all pretty familiar, hopefully. OK, so next up we have the equijoin. Equijoin is a subset of a theta join. So all equijoins are theta joins, not all theta joins are equijoins. There's different ways that we can write the equijoin as expressed up above. But an equijoin is just a very specific type of theta join because you are looking for equality and only equality, which is weird because it uses the theta symbol in there, but the theta symbol wasn't used for the theta join, it was a C. And for the equijoin, we're using the theta. Anyways, all you need to know is that equijoin must be equality. That's what it's looking for. And it's right there in the name, as it says so on the tin. So it's not a very difficult concept to think about. It's just a very specific way of expressing a join. So this is the inner join that you're all used to from SQL, where we're looking for equality. And this is honestly I think it is fair to say it's the most common variant of an inner join that you'll see either in practice writing SQL or in the theory and relational algebra, because typically when we're dealing with relations, we have that foreign key that we can rely on, and we're going to use that to check for equality when we're doing our filtering on a join. So this is a pretty important type of join to understand how it works. It's pretty straightforward, though. Any questions so far on this one? And if you got theta join, this is pretty straightforward. It's just a very specific version of a theta join. OK, now the slightly tricky one is a natural join, which we'll talk about next. But just to give you some, again, an example of how an equijoin works, this is an example of it. You can, of course, create the cross product like in the previous example if you want to look at it and be sure. But in this case, we're just taking ABC and DBC and we're joining them together. And of course, we're looking for the B and the C attributes must be equal across both tables. So this would be looking at kind of like maybe two foreign keys. You can think about it that way. So this is the reason why we only keep these two tables. U.B and V.B both are 1, 1, and 5, 5. And then U.C and V.C are both 9, 9, and then 9, 9. So this is just the same thing as a theta join, but we're looking for equivalency. Any questions? Okay. The natural join. This is a way of doing a join where you don't have to explicitly state any conditions because the natural join looks for attributes with the same exact name. Note, not like you have different aliases or anything. The attributes have to have the same exact name and they have to have the same exact data type. So natural join looks for, in both relations, same name. And if it's got the same name, same data type, and then it chooses to do the join on those. So you don't have to specify any conditions. And in SQL, you can do a natural join as well. The only problem is that I will strongly recommend that you never use a natural join in practice because a natural join in practice is extremely hard to read. It is not really apparent what you're trying to do. You have to have a complete context of the underlying attributes in the data as well. So if you have a natural join that's part of a complex SQL query that you're writing, you have to understand at what point the natural join is being run and what are the attributes it's being run against to understand what's going on. Also, these types of queries that use natural join don't have longevity as code because as soon as the underlying table starts to change, perhaps there's an attribute that's renamed or there's a new attribute added that has the same name as in another table that you're joining to, you can get incorrect results of this join. So this join is important to understand how it works and it's good to use in relational algebra, but I would not, I'd refrain from you using it in practice when you're writing actual SQL. What's essentially happening here is R1 and the natural join R2. So on the left-hand side, that nomenclature, just using the join symbol by itself, is expressing that you're using just a natural join. Again, because there's no conditions on there. If we want to decompose this and try and write more verbose relational algebra, I suppose, to explain what's going on the right-hand side, this is mostly what's going on. You're doing a cross product between R1 and R2, and then you were selecting for some filtering, and that filtering is based on the equality of the columns, but instead of just being equality of the columns like the values, we also have the additional idea that the column names must be the same, and that's expressed in the outer one with the pi symbol. There, you're also removing duplicates too. So if you have two columns with the same attribute name and the same data type, you're going to join on those. And of course, whatever is the same in those, you're going to keep. And then you're going to drop one of the duplicate columns because they're the exact same thing. You won't need them. So as an example, in this case, we're going to check for attribute B and attribute C, and that they're going to be the same. So we only have one attribute A and one attribute D, and both tables have a B and a C. So we first join on B and C. They're the same data type, they're ints, and they're the same attribute name, so that's good. And then we're going to look for where they're the same. In this case, B and C in U is a 195949, and in V it's a 195932. So the first two rows in both these tables will come through, and that's where you get the A and the D of 3, 6, and 9, 7. And then, of course, we're going to have duplicate B's and C's, but since they're the same exact data, 1, 9, and 5, 9, we'll just remove one of the B's and one of the C's because we don't need it. So this is how the natural join works. And again, it's doing a lot, and it's got a lot of restrictions on it. And it is true that it is a very specific type of equijoin because we're looking for equality. But in practice, it can be very confusing as to how this works or what it returns to you. So I would not use these. It's interesting because this is an extremely explicit way of doing a join, but since you don't have to actually write the explicitness into the query language, it becomes very difficult to follow along and read it. So I would not use it in SQL. And I've never had to use a natural join in SQL code that I've written once. So you don't have to use it. Any questions on the natural join? We all understand what's going on? Does everybody understand the concept of why a theta join is a superset of the EQ join, which is a superset of the natural join? Does that concept make sense to everybody? Any doubts? It makes sense from a logical point of view as well as from like a fundamental constructive point of view of how the query is working and what the logic is? Yeah? Okay. Not too bad, right? Not that difficult? Cool. Someone's looking at me like I'm crazy right now. But I promise you, it's not that bad. It's just, like all these examples are very easy. You're like, oh, this is easy stuff. Yeah, of course. But when we introduce like more complex queries, like we'll show you in the demo and stuff, that's when the stuff gets difficult because you have to be able to use a bunch of these relational algebra commands and keywords together in order to do something that's more complex. But fundamentally, every operation in relational algebra, you already know how to do from SQL, more or less, or the logic behind it is not entirely too complex. So as long as you take it step by step, you break down your queries into very simple steps that are writing the relational algebra for them is not entirely too difficult. So just to recap, these are the three types of inner joins we've talked about, and their nomenclature, how they're written, and the cases in which you would use it and how they work. And then again, as a recap, just so you have them in your lecture slides nearby, here are the main set semantic relational algebra. Of course, all these things can be done with sets. We're going to learn about some additional relational algebra syntax today that works on bags. But all this relational algebra that you do in this class will be on using bag semantics, not sets. OK, so let's see. Yeah, OK, so this is just explaining to you that, think like PEMDAS, right? Please excuse my dear Aunt Sally. I think that's how it goes. Like order of operations and stuff, since this is an algebra, there's an order of operations, and you use parentheses and stuff to kind of set that precedence. And then here's some examples where you can combine them. So yeah, the very bottom one, let's see, pi. OK, so we have two single queries up top, and then we have combining both of them on the bottom and how that works. So we're doing a selection from the movie table on the left-hand side where budget is greater than 200 million, and then we're doing a projection that we want the name and rate column, and this is just combining both of them. In this case, from the movie table at the bottom, we first do our selection, which filters the rows, and then we do a projection, which filters the columns, and that's why we get name and rate. So just an example of using them together and how the order of precedence is executed. OK, so are you sick of inner joins? Because I sure am. Let's go to outer joins. OK. I don't think we need a break. I think we're all good. Pain train continues. OK, so outer joins, there's three variants of the outer join, the full, right, and left, and this is their specific nomenclature. And be careful when you're reading it because it's easy to miss these little like hooks that come out for the left, right, and full join. It's just a slight different version of the join character. OK, so here is an outer join, and we see R1 here, and what's that join symbol? Go back. It's a left join. OK, so this is R1 left join on A1 equals A2, and that's pretty much it. It looks and works exactly like you would expect in SQL. So yeah. So here's an example of it. In this case, we're going to take the acted in and the movie tables, and we're going to do just a very simple left outer join on both these tables, in which case, since planet Earth does not have any actors that fall in the acted in table, and I mean, I didn't put it in here. You should be explicit, but of course, the only two things to join on are name and movie name. So I didn't put that in there, but you would want to. But this is why we have nulls in planet Earth, because there's no actor for planet Earth that falls in the acted in table. So this works exactly as you'd expect from the relational algebra that you've done equivalent in SQL. No different. And this works exactly like the inner joins, except you're doing inner joins, except now you're doing outer joins. Left and right are still inverse of each other. That's correct. And the full outer join, of course, when you do full outer joins, you most likely, unless all the conditional logic is true, you're going to have nulls in two axes, both along the horizontal and the vertical axis. Whereas if you just have a left join, you'll have nulls only going in one axis, and if you have a right join, you'll swap that axis for the other side. So that's sort of how the nulls work with these joins. And this is different than the slides that you have, but the tree for the slides that you have had a mistake in it that I didn't like because it showed equijoins. One, it didn't include natural joins. I think it had equi and theta joins on the same level, but they're really hierarchical. So I found some new ones for you guys. And this chart on the right-hand side is just a nice way to read through what your current problem is and what kind of join you might want to use. So if you're having any doubts or difficulties, that type of flow chart can give you some information. Yeah, any questions on outer joins for relational algebra? Yeah. So good question. You don't need to do the cross product when you do outer joins because the assumption is that one table has more or equal than the other table, and you're just going from left to right. Forget about right. I don't know anybody who writes right joins. It's always people who write left joins and you just change the columns. So just think about joins from as a left outer join. I don't think we don't have any homework or exam questions that are right joins, right? No, I don't think so. So just think about left joins. When you think about it, you're just taking one table and you're just kind of moving across and you're sliding, and whatever whatever matches that criteria comes over, and whatever else doesn't is just a null. So there's no reason to do the full cross product there. Where in an inner join, you want to do that in order to catch all of the potential equalities. I mean, I suppose you could still do it, but you don't really think about it that way. And of course, too, in outer joins, you can also have a left outer theta, left outer equijoin, so on and so forth. All that depends on is what type of condition you're applying to the join, whether you're looking for equality or inequality. Then I suppose it kind of surmises what specific type of outer join you're doing. But no one ever says like, oh, I'm using a right or a left outer equijoin. Certainly not in SQL. In relational algebra, we don't really care as long as you're saying you're doing a left or a right or a full outer join, and then just whatever condition you have to apply to it is fine. But I suppose that the table on the left-hand side makes that tersely explicit for all of you. But good question. Any other questions on outer joins? No, okay, then this shouldn't be. This stuff should be pretty good to go. And what I really want to do is get into the demo so we can do more practice examples together and stuff. But this stuff should be pretty good because you've been doing SQL for a little bit now. And this is the benefit of doing SQL, I think, before. These type of classes are taught in two ways. One, SQL is what you do first, or relational algebra is what you do first. I find SQL first is more fun because you get to do stuff and you get to see the results. And it makes relational algebra, I think conceptually you have a framework in your mind that you can map on what these things are to it. But strictly speaking, relational algebra is typically taught first in these type of classes. But hopefully teaching SQL first made this a little bit more digestible and a little bit more apparent what was going on. Okay, so we go on now. I already talked about this, so I'm not going to go over it too much more, but we need bag semantics in modern SQL because we really care about duplicates. And this is the reason why you have the duplicate keyword in SQL, because you do get duplicates. And so you need to be able to, or sorry, not duplicate, you use the unique keyword because you do get duplicates that are returned back from joins and whatnot. And so you need to have some way to filter those out. Okay, so the main ones I really want to talk about are the duplicate elimination, so delta, grouping, gamma, and then sorting, tau. So those are the three that we'll really go over. You've already seen the other ones. They're just kind of new versions, spun in a different story. But if we look at duplicate elimination, so here we have relation R1, we're going to equal it to relation R2, but we're going to use this new fancy keyword that we've learned to get rid of duplicates, which will be delta, right? Yeah, delta. Okay, so not anything you haven't seen before. All we're doing is saying for every tuple in this U, we're going to create a new relation V and remove duplicates. So the only duplicate tuples we have are tuple 1 and tuple 3, which is also 1, 3. I like how that worked out. Yeah, so not too bad. We'll chalk that up to serendipity. Okay, aggregation. You can do aggregation in relational algebra. Remember, you can do these because it might make one of your homework or exam questions easier. But you can use constants. You can use these kind of simple aggregation statements. So sum of A is 1 plus 7 plus 1 plus 9, which is 9. Average, count, min, max. You can write these in relational algebra just as like in an aggregate or as a conditional or something. You just use the straight. There's no symbols for this. You just spell the word count out or something. This is not. There's no. So you'll learn something if you go online looking up more things about relational algebra. That sometimes the syntax that we're using is different from the syntax that other people use. There's not. Once you get past the basic relational algebra that we did from before to what we're doing now, a lot of the syntax sometimes is dependent upon who's writing it, and it changes. But this is the syntax that we're going to use, and these are things that we're allowing, like count, min, and max, because whether these are strictly relational algebra or not, they are simple computational elements of a system that supports a Turing-complete language, and so this stuff is all available to us. So there's no reason why we can't use it. So we're going to be using this, and you can use it too. So these are all, pretty obvious and easy. You just want to show that you can use these in relational algebra. Grouping, this one, you're just going to use this one keyword, and then you pass the list of elements that you want to group by. And that's pretty much it for grouping. Yeah, not much to it with the group by. So here's an example of using a group by and how you'd write it. So if we want to take this movie table and we want to group by the genre, and then we want to sum revenue, and we want to cast that as total revenue, and then count and name that as movie num, this is how you would do it. So yeah, we're just taking the genres and grouping them, and then renaming that as total revenue. And so in the group by, you can pass any number of extra aggregate. So whatever the group by you're doing, plus any aggregate that you want to add as well. So in this case, count, which we saw that we could use from this list here. So that's how you would write it, exactly as like count. The renaming and stuff, this might not work in Relax. I just wrote that there for, I don't know, maybe Nate can tell us. Is that, or do you have to actually use the keyword for to rename that? For total revenue and movie num? See how those are being renamed? Like that with the arrow in Relax?
In gamma only, yeah, you can do this. But only thing is it's a semicolon instead of a comma.
Oh, okay, so semicolon. Okay, so the syntax in Relax, a tiny bit different. But in principle, that's how you do it. Okay. And then, of course, sorting. Here we're just going to provide a list of elements to sort on, and it's going to do it in ascending order. Actually, for the relational algebra, it will depend on how it's sorted by the implementation. But relax will allow you to pass descending or ascending for sorting. Correct? Yeah, OK. So that's how that works. Again, not very difficult. And you'd pass the descending and ascending within the in the tau subscript as I think you can either a semicolon or a comma afterwards. And you can sort on multiple columns. Of course, the first attribute that you list first will take precedence, and then it'll work from there. OK. Before we talk about the tree stuff, any questions on sorting, aggregations, groupings, any of that stuff with relational algebra? No? The logic should all be very similar. It's just this new use of keywords and stuff that is probably the new thing. But it's all pretty much the same as what you've learned from SQL. And there's a reason for that, because all of SQL, any SQL you can write can be written as a relational algebra expression. So it makes sense. OK, we're not going to ask you to write your relational algebra as a tree, but in a relational database management system, every time you submit a SQL query, it gets translated into a relational algebra tree. In this case, we have the relational algebra in the green kind of box area, and then this is how it gets translated into a tree. Always at the root of the tree is the answer, and then it follows in a very logical way from that. So we have our base tables, acted in and movie. We know we're going to do a join at some point, but acted in has some selection criteria on it. So acted in gets a selection for Marlon Brando, and then we do a join on movie, and the join condition is the natural join, so we don't have to do anything else there. And then we do a projection for the genre attribute, and then that gives us our answer, so to speak. And there's the equivalent for SQL. So if you provided that SQL to the relational database system, you would get that relational algebra expression, which would be transformed into this relational algebra tree. That tree would be, well, there's other stuff that we'll talk about later, but that tree gets examined, and then it gets checked for syntax correction. It gets checked for logical correctness, and then it starts to query some of the tables, finding out what data it's going to need, and then it might do some further optimizations. It might even rewrite the query as a different relational algebra expression, which is logically the same, but might be more optimized. But it doesn't work off of your SQL. It always works off of relational algebra once you're inside the database system, as far as like how to actually get what data you're going to need and stuff. So that's how that works. Here's another example of how a tree might work with these intermediary tables. So here you have movie, and we're going to do a simple select from, and then we're going to group by genre, and then we're going to apply some logic to the group bys, and then we're going to finally have a select for the summing the revenue and counting the number of movies. And in this case, there might be two temporary tables. So the first dotted line might be like T1. And in that case, you would set whatever was the group by from the movie to T1, and then you would do your selection from that, where the total revenue needs to be above 1 billion, and then you set that result to another temporary table up above, and then that temporary table would have a projection on it, which would then give you your answers, or your answer. So that's another way that it can work too, where it makes these temporary tables. Those temporary tables could be stored on disk sometimes, or sometimes they're ephemeral, depending on the size and what's needed. But they're always temporary, and they get cleaned up at the end of the SQL SQL execution. Let's see. Here is like a typical view of a select project join query, so like a select from where, and in which case you have your tables. They have some join condition. There could be additional join conditions, and then selection and projection. And this is where you kind of see a typical occurrence when you're doing joins, that it just sort of fans out. And this is also the reason why lots of joins can be computationally expensive, because you can calculate the Cartesian product for each of these joins that you're going to do if you want to calculate a cost, let's say. And the relational algebra, or the query optimizer, engine within the relational database system will do these calculations and see what's the total computational cost and time expectancy to run this query. And from there, we'll begin to make optimizations. But it makes a lot of sense when you view it as a tree and can kind of start to see what it's going to cost to run this kind of query. I think a relational algebra statement by itself, it can be very difficult to see logically what's going on and how to optimize it. But if you do turn it into a tree, it becomes a lot simpler to see where the potential for optimization can occur. And the potential for optimization is twofold. One is that us as users can see what's going on here. And if we have a particularly nasty query, we might turn it into a relational algebra tree and see if there's opportunities to provide filtering or some sort of conditionals before the joins. So we might want to write like a common table expression or a subquery to produce a smaller table to join with. That's one thing. The second item of why this is good is that the optimization engine can use this and it can see the individual statistics of the join operations and try and look for optimization. One of the big causes of optimization in relational database systems is bad joins. Joins that are very unnecessarily large, or joins that also include extra columns or attributes that you don't really need. If you're going to do a join and take extra attributes that you don't necessarily need in your output, just for say, you just do the select star instead of selecting the actual attributes that you need, that's a really good area for some optimization. The more attributes you have that you have to carry with you throughout this entire graph, the more computationally complex all of the calculations become. Second, if you need to do a join and those two tables that you're joining are very large, it is extremely cost prohibitive. If you can rewrite your SQL to be able to do a filter on one of those tables ahead of time to make them smaller, your join operations become much smaller, and that can be a great way to reduce the total cost of your query. So being able to write relational algebra expressions as a tree and evaluate them compared to your SQL code really can help you to see the cost of what's happening and to try and find better ways to optimize your queries. And we'll talk a little bit about other strategies to optimize this cost. There are tools out there that can give you a graph-like tree structure view of what your query is doing, and you don't have to actually write the relational algebra, and these can give you also beneficial ways of optimizing your queries. And yeah, Vinith and I have some cool stuff to show you for that. That's actually Vinith's favorite lecture, it's the optimization lecture. He loves optimizing. So yeah, this is just another example. I'm just trying to give you some of these trees so you can see how these simple SQL queries are represented in a relational algebra tree structure. But I've already kind of gone over this. And of course, you also, I guess one thing to add is the order of operations in which the SQL statements tend to be executed off matches very nicely, which makes sense in the tree. Where, like, for example, the halving condition is one of the last things. Well, at least in this case. Okay, any questions on any of these, like relational algebra trees and the importance of them? Again, I don't want to spend a ton of time on them. I'm not going to ask you to do them, but I want you to see that they exist and understand that they can be important. Nope. Okay. So let's talk a little bit about subqueries because it's everyone's favorite subject. Here is a correlated subquery where we're looking to check for actors who have acted in action movies and who have acted in drama and to try and find the difference between them, essentially. So we have two subqueries here, one that gets the actors in action movies and then one that gets the actors in drama movies. And then we look and see for actors who are in action but not in drama. And so this is certainly a correlated subquery because the action and the drama tuples that we're creating are going to be checked against whether or not we want that actor in the final result in the outer select from where SQL statement. However, we can decorrelate and unnest this query by using an except statement. So why do these two subqueries when all we want to do is get both sets and then get the difference from them as a set operation? So nothing new here. We've seen this before. But how would this thing be represented as a relational algebra tree? And this is how it would be represented. So in this case, you have a set difference, which is the very top level result that you want to get, and that set difference is on two different tables. And in this case, both those tables have their joins in order to get the movie name and the actor name. You want to join to get the genre so that you can know if that actor was in a comedy or in a drama or an action genre. So you can represent subqueries in relational algebra as well as kind of set queries. Again, just further proof that there's not a single valid SQL query that you can write in this world that you cannot express in relational algebra. If you could, then it would break the very basis of how relational database systems work and how they're engineered. So the whole point of it is that relational algebra can express all of your SQL queries. And they are always transformed into relational algebra whenever you submit a SQL query to a database optimizer engine. Okay. Yeah, so that's pretty much it for relational algebra. Let me see. I have some notes. I covered most of the stuff. Yeah, I can't express how important it is not necessarily to be able to write relational algebra on your job, but to understand logically like what is happening to a SQL query. And if you understand relational algebra and it's like tree-like structure, then all of a sudden when you look at a SQL query, it's not just a collection of SQL statements anymore, but there's like a logical sort of force to it that you can look at and think about, and that really helps you to write good quality SQL code. Because part of being a good data scientist is being able to write optimized SQL code. It's just something that's a nice skill to have, and knowing relational algebra kind of gives you some insight into how to optimize that type of code. Okay, any questions on relational algebra or any stuff that we covered so far with the outer inner joins? Okay. Let's go ahead and I'm going to ask Vineeth can get his demo started. One last thing I want to show you. I guess he's already ready, so maybe I'll just show you this real quick. This is a submission from one of the, this is from a homework, right? Homework 4. This, okay, was the answer to one question, and this is page 1 of 3. Okay, so just because you know relational algebra does not mean that you can still write good SQL queries or good relational algebra queries. Like, and we checked this. This actually worked, okay? Did they get full credit? No, they didn't, okay? Because this isn't math. I don't care about the right answer. I care about how you got the answer. Because this is engineering as well. And writing unoptimized, sloppy relational algebra code because you don't understand something fundamental about relational algebra is not the way to get the right answer. You know, this is the result of somebody who didn't understand the fundamental properties of relational algebra. And so all of a sudden, they've got a hammer and everything looks like a nail. If they understood the concepts of like using aggregates and constants, then this becomes like 4 lines of relational algebra code instead of like 60 or something. So, you know, I don't know, I put this up there to scare you all too. I think Kavya was like, oh, don't put that up there, you're gonna scare them. And I was like, no, we need to scare them. But yeah, I mean, you know, this is just like, look, these T15, T4, like they're just making temporary tables with stuff to try and do these like insane calculations in order to be able to do a final join at the end or the right. And look, they've used a right outer join after I said I hate right outer joins. You just left outer joins. Anyways, so yeah, just if you're writing this much relational algebra code, you're doing something wrong. You don't have a good understanding of maybe the problem or something. So just you know, if you're getting like 10 lines in, stop and take a break. But don't do this. Okay, so yeah, we'll go ahead and do some. I want all of you to have the opportunity to write some more complex relational algebra and to work through it. So and then we can sit down and talk through it together and make sure you guys have some examples. because it's hard to have like a lot of examples of this stuff. One thing you can do to study and practice for relational algebra is you can take SQL statements that you already know are the right answer, and then and that you've kind of forgotten how to write them because maybe it's been a week or so. Take that question, put the data into the Relax engine, and then try and write those queries as relational algebra, and then check them against your SQL queries. That could be a good way to study this stuff as well. But, OK.
So we'll take a look at how you can use Relax to understand relational algebra. So we've been using this toy movies database, in all the lectures, right? I believe you have access to the student version of this, right? So the idea is that you want to be able to insert this database into Relax. So what you can do is, you can just go to the calculator here, right? And not a lot. It's very few.
Not that many?
Yeah, just a few. This is a sample data set. So the idea would be something like this. We'll give you a sample data set for your homework or like say your final exam, and then you can play around with it, but we'll use a much larger data set when we're auto-grading, so your queries may or may not work, so make sure it's, works in all situations, right? So yeah, basically what you do to insert data into Relax is you kind of put it in this format. You say group : and then you give some name to the data set, like say movies data, and then you put in the table name, right? So in this case, acted in, and then equals, and then open the brackets, put in the column names, and then for each column, like you put row-wise data or tuples, right? Same thing you do for the other tables, like movie table and rating table and so on, right? So,
huh? Does he use a new-line character at the end? Or does it just know by the number of commas?
For what, sorry?
Does it have a new-line character at the end?
Yeah.
It is, okay.
Yeah.
So make sure you put a new line, and that will tell it that's another tuple.
Okay. So if you just copy this and go to the group editor here, here you can see that your query goes here, it says. So you just copy paste this. So you have it in this format. It automatically detects what the tables are. So you can just click on the table and see what the acted in table contains, right? And you can do the same for the remaining tables, make sure it's correct. Click preview also, and it shows you all the information from the tables, right? And once you have preview, so you paste it, you click preview, then you have to tap this use group in editor, okay? So you'll observe that now you should have all the tables on this left side here, okay? So you'll have the acted in table, and it auto detects what type it is. So in this case, it's saying that actor name is string, movie name is string, salary in million is a number, and so on, okay? Yeah, so once you have this, then you can start writing your relational algebra query related to the database or the tables. So I'll just pause for a second, let everyone catch up, and like if you're facing any issues, just let me know. Yeah. Yeah, copy pasting.
Yeah, put it into a text editor.
Yeah, first put it in a text editor, and then I don't know why the PDF version is bad. Maybe we can release the Markdown versions.
Really, just give a file, a text file with it.
Yeah, I can just paste it on Piazza, I guess.
If not, just put the the copy paste text into like a VS Code tab or a Sublime or Vim, and then paste it from there, because that'll get rid of the special characters and the extra spaces.
Okay. Okay, I just posted it on Piazza. Yeah. Oh.
Yeah, I want their phones to blow up.
Oops. Class notes resources. Yes. All right.
Let's see their phone on.
Yeah, so you can just copy this and paste it. Okay. Yeah, I'll just give like a minute or two.
Yeah, we have like 30 seconds or so. I mean, it's just copy paste.
Yeah. Okay. Yeah, so if you look at the calculator or relax calculator, you can see that it has all these various symbols, and you can also see how you can use the symbol. Like either you can click on it, for example, in this case, you can click pi and it automatically inserts pi, or you can take a look at it, know that it's pi, you can just write. You can also type in pi or sigma or any of the relational algebra operator that you want to use. So in this case, let's say you want to look at, all right, we start off with, okay, let's do this. You can start off answering these simple ones. Find the names of all movies that Marlon Brando has acted in. Like you can try it out, see if you get the right answer, and then we can take a look at the answer. Okay. I have another one actually. Okay, anyone wants to give the solution for this? Find the names of all movies that Marlon Brando has acted in. Oh, it's not that difficult. I hope not. Anyone want to help me out in this? Yeah. Uh-huh. Okay. Selection.
Let's start in SQL.
Yeah.
Who wants to do a SQL for this?
So the data that we have looks like this. So you have a movies table, you have a rating table, and you have an acted in table, right? So movies that Marlon Brando has acted in. Okay. Yeah. You don't have to do distinct because our acted in table does not have duplicates. Like the actor name and movie name pair will only come up once, right? At least in the toy data set that we're using. But yeah, so if you look at the SQL query, pretty straightforward. Select movie name from acted in, where actor name is Marlon Brando. Same thing, can you convert to relational algebra?
So what are the two operators for the select and the from? And so the select and the where clause. Yeah.
Mm-hmm.
Yeah, so we're doing a projection and a selection.
Mm-hmm. So you look at it from internally, like, so you start from the inside first. So you say sigma actor name equals Marlon Brando from acted in. So you're selecting the actor name as Marlon Brando from this acted in table, and then, or sorry, selection, not selecting, but yeah, selection, and then you're projecting, right? So you're doing a projection of the movie name. So if you were to write the same thing, so with relax, it would look something like this. You say pi movie name and then sigma actor name equals Marlon Brando. Here, it does not, I mean, the spaces for some reason. So if you try to copy paste, the spaces cause issues, okay? So it's recommended that you type it out. It's not a perfect, yeah. So for some reason, the copy pasting in relax causes issues. So make sure that when you're using relax, you type it out because the spaces, even though they look fine, the spaces will be the ones causing the issue.
Actually, this is a really good data science tip. So you will, at some point in your lives, have to parse
100%.
and the data will look great, and it will tell you that it's wrong, and you will
break your head
on it. You need to check for non-printable characters, which are invisible, but it's very easy. And sometimes non-printable characters get written to a database. So you might have a first name, space, last name with an unprintable character, and it will cause you all sorts of headaches. So just remember the word non-printable, or the phrase non-printable characters. It will save you like 4 hours.
Maybe more.
Maybe more.
So yeah, it looks normal to you. Like in this case right now, I copy pasted it, but it's throwing an error here saying that it's expecting something. You have no idea what's going on. This looks completely fine, right? So this is a problem that you might face in the future at some point. You will face it at some point. But yeah, so the issue is that the space here is incorrect. There's nothing wrong with the query as such. It's the space. So just clicking backspace and actually putting the normal space for each of the space here, that fixes the issue. So we can just execute this query. And you can see that this is how the tree kind of looks. So first, it started with the acted in table, right, which had 9 rows. And then it selected all the, you did a selection where you said the actor name is Marlon Brando. Now you're left with 2 rows. And then you projected or did a projection to get the movie name. So this is how it looks. And it also gives you, if you click on a particular, so you can see step by step that if you click on, say, acted in, it starts with all this. Then you can say that, you want to look at the actor name selection. This is how it looks like. And then you look at the projection, final projection, and this is how it looks like. Yeah.
There, just so that they can see it.
Yeah. So
you don't technically have to have the parentheses in this case, but I recommend always adding them because it'll keep the logic flowing a little bit easier because you'll see what's getting operated on first. And that leads more naturally to thinking about it as a tree anyways.
And yeah, you can see the syntax here as well. You can use either of the syntax using brackets, without brackets, but recommended to use brackets just so you know, it's easy for you to understand. But yeah, that's query 1. Let's see how we fare with query 2. Find the names of actors who've acted in movies with a budget over 100 million. This also shouldn't be too difficult.
But it does require join.
Just building step by step. Don't worry, we'll get to the harder queries.
Maybe we should show them the slides.
This is just to get you familiar with relational algebra. So maybe. What do you have in mind? I open my YouTube music. If I open my YouTube music. It's on. Okay, anyone has the solution? Shouldn't be too difficult. So this is how the acted in and movies table look like, or you can take a look at it through the eyes of relax. Right? You can just see the structure here. So where's the budget at? Budget is in the movies table, so you know that you need the movies table, but it's also asking you, find the name of actors who have acted, so you also need the actor name, so you know that you have to join those two tables, right? So for the join, so I mean, for me, I always try to go backwards, so I kind of start with SQL and go backwards, but technically the idea of relational algebra is so that you don't know anything about SQL and you start, but since this is an introductory course, it's okay to think of it this way, right? So this is what you'll do in SQL. You just say select actor name from acted in, join movie on this movie name equals movie.name, where the budget is greater than 100, right? Because the budget is in million. So this is how it will look like in like LaTeX math format. So this is how you would write it. Either of these are acceptable. And then this is how it look in relax. Probably add a few more brackets, but again, same issue. I hope there we go. It's the same issue. Let's see. I have to do this for every one of them. Oh, fair. I'll do it for the next one.
Okay. In fact, you can roll the VS Code while they're working on the next one.
Yeah. So you can see how the join works. So in this case, what we're doing is, and this is the advantage actually of relational algebra if you were to try to do this. So you see that in this case, you're doing an acted in and movie, right? And you're joining both of them, okay? And you're getting 7 rows here, okay? But the problem is there is a slightly better way of doing it. Can anyone figure out how you can write this query to perform faster? Let's assume that the acted in and movie table had very large number of rows, right? And they had that's the idea, yeah. So it's always better to join smaller tables than join 2 big tables and then try to filter something, right? So this kind of control you don't have exactly in SQL. You'd have to have like a nested query or something and then you join it, which is possible. But in relational algebra, because you can add the where condition anywhere, right? You can always put it at any point. So in this case, you have more control over the way you write the query. So in this case, you would add the sigma to the movies table first, and then you would join both of them. So you have a smaller join, right? You're joining 2 smaller tables. You can kind of simulate this in SQL using like nested queries and using the common table expressions, right? But yeah, this is how it would look. So it'll give you movies and acted in, and it gives you the condition that then like the acted in movie name is equal to movie.name, and then you select the budget, and then you get the actor name, right? So this is how it would look. You can add in more brackets. So after actor name, you do this and this, right? So that looks better. But of course, this gets cumbersome, right? So we'll take a look at a better approach to this. Okay. So on to the next. Find the average rating for each movie. Of each movie, yeah. Not too difficult. So the only reason we put this up is typically in relational algebra, you do not have access to these kind of averages or aggregations in general, right? Reason being, relational algebra is like a basic thing that you build everything on top of. So the idea here is that Relax does support extended relational algebra. This is what it is. And the idea is just like the SQL query is simply just select movie and average rate of the rate as average rating from rating, and then grouping by the movies. If you want to look at the relational, yeah. Let's see. Okay, so we wanted to find the average rating of each movie. So each movie can have multiple people who have rated that movie, right? So what you do is you take this rating, you group by the movie so that you get all the reviewers for a particular movie or like all the ratings for a particular movie, and then you take the average of the rate, right? So in this case, we'll be using the gamma, and here it is slightly different. So in relational algebra, you do not have a having clause in relational algebra. The reason being that you can use the selection or sigma anywhere, right? So technically what you can do is you can do the group by first, right? Get the information that you need, and then you can do the sigma on that whatever extra column that you create with the group by, okay? So in this case, this is how it will look like in relax. Okay, looks simple. Okay, it works. So in this case, what you're saying is, right, so when you use the gamma function, you can see how it works. So let's go click on gamma here, just like hover over gamma, and you can see it says gamma a comma b, and then semicolon, and then count something, and then it gives an arrow, right, and then some letter, and then it says a, right? So what this essentially, if you're not able to understand this, of course, this might be tricky to understand, you can always go to the help, right? So if you just click on help, you come here, and then you just search for gamma, okay? And it says group by here, okay? So in this case, it gives you the argument is a list of columns to group by, separated by commas, followed by a semicolon, and a list of aggregate functions to apply with their new name in form aggregate of column, and then you give some new name to that column, okay? So you read this documentation, you understand what is happening. All it's saying is gamma and anything you put before the semicolon is the group by that you use, right? All the columns that you group by, and anything after the semicolon is all the aggregate functions that you have to do on the other columns, okay? And you have to make sure that you give them a unique name, right? So in this case, what we're doing is we're saying group by movies, right? And get the average rate of all these grouped movies and name that column as average rating, and do this on the rating table. That's essentially what you're saying here. So when you execute this query, you can see this is the output that you get, right? So you have all these different movies, and you get the average rating for each movie based on the ratings table, right? And yeah, the rating table started off with 12 rows. That means we had multiple ratings for each movie, and now we have 8 rows in the group by, which gives you the average rating, okay? Any doubts up till this point? Clear? Okay. So I think we can skip query 4. Yeah. Yeah. So query 4 is pretty easy. It's just 2 sigmas. I mean, you can use an AND or a logical operator. So let's go to query 5 and 6. I feel like query 5 and 6 are more interesting. So for query 5, find actors who have acted in at least 2 different genres. Probably give like a minute or two, see if you can come up with a solution for this. Next one after that. Anyone has any ideas for query 5? How would you start? What would you do? What's the first thing that you think of? Yeah. Mm-hmm. And then?
You need to group by actor name.
Mm-hmm.
And you count the number of genres.
Mm-hmm.
Then you select the ones that are having reviews.
Mm-hmm. And yeah, that's correct. That's pretty much it. So yeah, so the SQL query looks like this. All you do is, you join the acted in and movies table, and then you group by the actor name. Okay, so that will give you all the genres that this particular actor is acted in. But the problem is you're doing this having count of distinct genres being greater than or equal to 2, because that's what we need, right? At least 2 different genres, right? The problem is if you try to, say, run this SQL query on, say, Relax or anything, you don't have a concept of distinct here, okay? So it kind of throws an error. Maybe you can try moving this and name it as, like, say, count or something. Okay, count, and then say that count is greater than or equal to 2. It still doesn't work, because the way Relax works is whenever it does a projection, right? That means you're using the select statement, it automatically does the distinct for you, okay? So you need to be very careful with that. So sometimes you may not get the answer that you want. If you use a gamma instead, it selects everything. But if you use a pi, it selects distinct. Okay, that's a small difference. In this case, this will work because for each actor we have a different genre, and you will get some output like this. But if you need to get distinct genre, then query. Okay. Would this be correct? I have to again. Oh, sorry. Thank you. Okay, there we go. Okay, would this be correct? So what are we starting off with first? Okay. What does this do? Okay, can anyone tell me what does row do first? Okay, yeah, it renames. So in this case, we are actually renaming the whole table. So row also allows for renaming of a table, not only columns. So what we're doing here is this is grouped together. Okay, so you can say that this is in one bracket, which is row A acted in, and then we're also having this, right? We're saying that rename movie and acted in as M and A respectively. Okay, so once you have this, then I'm saying join on the condition that A.movie name equals M.name. Okay, so that is what we're storing in T1 in this case, right? So and then in T2, what are we doing? We're doing the group by. So we're taking the actor name, we're grouping by the actor name, and counting the genres that this person is acted in. So will this work? We didn't use a distinct technically. What's happening? There we go. Okay. Okay. How would you? Oh, so we're not using a distinct anywhere, right? How would you remedy this? Anyone has any solutions for this? Okay. So in this case, luckily, it gives the same answer if you use a distinct or if you do not use a distinct, right? So what would you do in this case to make sure that you have distinct? Unfortunately, we don't have the delta operator here in Relax. Okay, so the one you learned in class lecture for delta to remove duplicates, that's not available to you. So what can you do? What did I tell you about selection versus, the selection in relational algebra? What does it do? Or sorry, the projection in relational algebra, what does it do? Okay, so The projection in relational algebra, like I said, does remove duplicates. So the idea being that, once you get this T1, right, you create a temporary table. Let's name it some Tn or something, okay? And then you say that, okay, you select only the required items, right? So which is pi a dot actor name and then m dot genre, okay, of T1, right? And then instead of using T1 in this case, you just use Tn, right? So this will work because what you're doing is you're taking unique, distinct pairs of actor name and genre, right? So that's what you would have in this first case. And then you take the distinct pairs of actor name and genre. That will remove all the duplicates. So once you have this, then you can do the group by, where you group by the actor name to get the count of all the distinct genres that you have, right? And then you can say that, select the ones that have a count greater than 2, right? Is this clear? Is there any doubts? Or?
His hand was up, maybe.
Okay.
Maybe not. Maybe just wait for that.
Okay. All right. So one last question. I'll leave it to you guys. We'll put it up on. This is more trickier. Find actors who have acted in all the genres. This is something that we covered in one of the previous demos, where we used count distinct, I believe. Mm-hmm. I think this one. Is this the one? Quantifiers? Oh, just one before this. Yeah. No, I think in this one itself. So I think we did, find actors who have played a role in all genres, right? So we took a look at this particular query, right? So see if you can try and replicate this in Relax. Okay. Any doubts up to this point? So this was how it would look. In this case, there was no difference in choosing the distinct, right? T1 versus Tn are exactly the same. Both have 7 rows. But in case there was an actor who had acted in multiple movies which had the same genre, then this would cause an issue, right? Okay. I think that's it. We're done.
If there's any questions, finish a minute early. Remember, don't come to class next Thursday.
Mm-hmm.